My goal today is to provide a solid introduction to the idea of resting membrane potential. This is one of the primary core features that I think you'll learn this entire semester, and it's vitally important that we understand how to set it up. But before we do that, I think it's equally important to recognize why we even care. What is resting membrane potential and what is its use? Well, to understand that, consider, if you will, two neurons, right? Your brain is composed of 80 billion neurons, and while this is a significant oversimplification, um, it is important to fundamentally understand how neurons talk to each other. So here we've got two neurons lined up in series, and everything from skeletal muscle movement to memory to emotion, it's all based on how these two cells interact with each other. And the process of interaction is called an action potential. And an action potential refers to an event inside one cell that essentially results in that cell releasing into what's called the synaptic cleft, a neurotransmitter. These little red dots are neurotransmitter. And those neurotransmitters bind to the neighboring cell and cause that cell to do something. In other words, this signal represents a communication between these two cells. That's what the action potential is all about. It's how neurons communicate with each other, or how neurons tell a skeletal muscle to contract. And while we're not going to talk about action potentials today, that's for next time. It's fundamentally important that in order for an action potential to begin, the cell has to begin at rest. The cell has to be in a state at rest. And that's what we're trying to understand when we talk about the resting membrane potential, where a cell rests so that it can do all these cool things when called upon to do. So now as we consider the resting membrane potential, I've broken this down into two simple steps. And the first one is to simply run the sodium-potassium pump. Now, that might seem like a simple thing to do, but I want to make sure that we understand the purpose behind it. To do that, let's come over here and let's take here's a cell membrane. Here we've got the outside of the cell. Here we've got the inside of the cell. And let's say back in the very beginning of time, as all this stuff was getting set up, we had equilibrium. Equilibrium, we talk about it as a state of stasis, of equal rates going back and forth. Of course, you and I want to avoid equilibrium because equilibrium for you and I is synonymous with death, and that would be a bad thing. But at equilibrium, we're going to assume that for every positive, and I've got those positives, for every positive, I have to have a negative. I'm not a charged individual. It'd be nice to be able to walk around and charge my phone just by sticking it in my pocket, but it doesn't work. For every positive, I have to have a negative. And that means also that on the inside of the cell, I'm at balance. And so I also have those same positives. These are, of course, represented by ions. These same positives and these same negatives. Now, as we think about this, let's identify some of these. The positive, we're going to call this sodium ion. The yellow one, the yellow positive, we'll call this potassium ion. And the negatives, some of it's going to be chloride, but most of these are just actually negatively charged proteins inside the cell. Okay, so this represents equilibrium. Well, why then is our first step to setting up resting membrane potential to run the sodium-potassium pump. If you recall from our previous discussion, one of the key purposes of primary active transport is to establish gradients. The sodium-potassium pump works, we'll draw it right here, by using ATP to pump 3 sodium out, and likewise 2 potassium in. Now this isn't a simultaneous event. This isn't like an antiporter. This is it pumping in one direction, then pumping in the other direction, then one direction, the other direction. Arguably the most important protein in all of biology, and I want to show you why. Let's just run this. Let's run it one time. We're going to pump 3 sodium out. So let's take these 3 sodiums right here, and let's pump them to the other side. There they are. Likewise, we're going to take 2 potassiums from the outside and pump them in. So we take that one, take that one. Let's put those down here. I want you to appreciate what we just did. We started to make a gradient. In fact, 2 gradients. Sodium is going to be high on the outside, low on the inside. Potassium, in opposite fashion, will be high on the inside and low on the outside. But I also want you to count the charge. Here, in the outside, I still have -10. But how many positives do I have? I have +11. And on the inside, I still have that -10. But on the positive side, I only have a +9. So after running this pump once, I've created a dipole across the membrane. I've separated charge. This with a +1 and this with a -1. Now, let's run it again. Let's take those 3 sodiums, pump them to the outside. And let's take these 2 potassiums, pump them to the inside. Now, let's quickly redo our math. We still have the same amount of negatives on the inside versus the out. But here I've got a positive 12, and here I only have a +8. That yields a +2 net on the outside and a -2 net on the inside. The term we use to describe any transporter that separates charge, like we see here, is called electrogenic. The sodium-potassium pump is electrogenic because it pumps an unequal amount of charge. It might be that I'm just pumping one thing in one direction. If that thing is charged, it's going to be electrogenic. I could also have electrogenic leak channels, right? As potassium leaves, as we'll see in a second, potassium leaves, I'm going to start separating charge. That's the idea behind something that's electrogenic, something that will separate charge. So we see that the sodium-potassium pump did 2 things for us. A, it separated charge. Not a lot, but a little bit. It got us started. B, and most importantly, it created two gradients. Areas where we have contrasting concentrations. So we see a gradient of sodium that's high on the outside but low on the inside, and we see a potassium gradient that's just opposite. Potassium is high on the inside but low on the outside. With that in mind, let's zoom out a little bit and see what this might look like inside a cell. There's my cell. If we review, we have our sodium-potassium pump. This is an ATP pump, and it's pumping 3 sodium out, and 2 potassium in. There's several ways that we can draw what this gradient looks like, or both of these gradients. We already determined that the sodium gradient was high on the outside to low on the inside. Maybe we could draw that also by saying there's a lot of sodium on the outside, big Na+, but tiny little bit of sodium on the inside. Likewise, the potassium gradient was low on the outside, but high on the inside, so it's tapered like that. Or big K on the inside and tiny little k on the outside. We can actually put numbers to these. In a typical cell, the sodium concentration is going to be close to about 140 millimolar on the outside, and on the inside, it's going to be about 7 millimolar. If we look at potassium, it's almost equally as strong. We've got 135 millimolar on the inside and about 10 millimolar on the outside. This helps us understand the basis of these two gradients. Now, there's one thing when we talk about gradients that's also essential to know. If we're talking about a charged particle, we want to understand and define the term electrochemical gradient. The electrochemical gradient has two components to it, the electrical part and the chemical part. It's important, we've just defined the chemical gradient, right? The concentration of the chemicals, high on the outside or high on the inside. And we know from our previous discussion that passive movement, passive diffusion, will always go down that concentration gradient. But when we talk about charged particles, we also have to take into account that opposite charges attract and like charges repel. Remember, when we were talking about the sodium-potassium pump, we said that it was electrogenic. That will yield a cell that is negative on the inside compared to positive on the outside. Now we have to think about this carefully because we see sodium. Sodium, based on its chemical gradient, like we show down here, sodium really wants to go inside the cell. That's its chemical gradient. Sodium is also a cation carrying a positive charge. And because the inside of the cell is negative, the electrical gradient for sodium is also inside of the cell. If we add up those two arrows, what we end up getting is a very large arrow that explains to us or predicts the desire that sodium has to get inside the cell. And it's a very, very strong desire. Now let's contrast that with potassium. Potassium, as we see, its chemical gradient is out. It wants to leave the cell, down its concentration gradient. However, potassium is also a positive cation. And every time potassium leaves, the cell gets more negative, right? It's a positive, it's leaving, it leaves behind negative charges. What that means is that its electrical gradient, albeit at these charges weaker than the overall chemical gradient, its electrical gradient is in the opposite direction. And that reduces the overall strength of the of the potassium gradient. But for all of the cases that we'll see in this class, sodium will still always want to leave the cell. It just doesn't want to leave as badly. Potassium will always want to leave the cell. It just doesn't want to leave as badly as sodium wants to come in. Okay, now that we've established our gradients, let's come back to the two steps to establishing resting membrane potential. The next step is very simple. All we have to do is open a leak channel for potassium, a potassium leak channel. Now, to highlight what this is going to do, let's come back over to this picture and let's come open right here a leak channel that is specific for potassium. Remember, a leak channel is always going to be open. The only way to predict the directionality through a leak channel is to understand that it's passive diffusion. Ions will always go down their electrochemical gradient. And for potassium, high on the inside, low on the outside, potassium wants to leave. Well, let's take a few of these and leave. Let's take this one. Now it's out here. And then maybe let's take another one. Now it's out here. What are we doing? You see quickly that the number of positives on the outside is adding up very fast. So instead of this being a 12, all of a sudden now it's a 14. And instead of this being a positive 8, now it's only a positive 6. And you can see how that's going to change these overall numbers. Now all of a sudden we're at positive 4 over here and negative 4 over here just by moving a couple of potassiums. This is how the cell becomes negative. Now, let's move one more. Same thing's going to happen. The outside's getting more positive, the inside becomes more negative, but this is where the electrochemical gradient starts to come into play. For every potassium that leaves, the cell gets more negative, and it's wanting to pull those potassiums back in, so it lessens the pull. So we're never going to really truly reach equilibrium in the sense that I'm going to have the same amount of positives on the inside as I'm going to have the outside. That's not going to happen. Plus, we're always running the sodium-potassium pump to make sure that those that leak out are just pumped right back in. There are enough doors open to maintain the resting membrane potential for any given cell. But this resting membrane potential is defined not by just moving some potassium out, but by a constant stream of potassium leaving the cell. What that means is if I increase potassium permeability, and by permeability, I'm essentially saying let's just open more doors. Potassium can't go right through the membrane. It needs a facilitator. So let's open more doors. If I increase potassium permeability, what do I get? The cell becomes more negative. But if I decrease potassium permeability, the cell becomes more positive. Let's go back to our picture of the cell and see what this looks like. Let's come down here to the bottom and open up a channel, a leak channel specifically for potassium. There's potassium, and we know that potassium will want to leave. So out it comes. We know that that's going to drop the cell to become more negative. So that the final concentrations, we've already got that listed up, the final concentrations 135 on the inside, 10 on the outside for potassium. For a given neuron, this will result in a resting membrane potential at about negative 70 millivolts. Now this varies. We could have cells that are more negative, like cells in the heart that are at minus 90, cells that are less negative, like cells in the gut that are at minus 50. There's a range. But this is a good average value and certainly average for neurons in the cell. They like to work at minus 70 millivolts. Now, let's test our understanding of this. If we understand how this works, then we should understand what would happen if things were thrown off balance. Let's take, for instance, some disease states. Let's consider hypokalemia. Hypokalemia is a state of decreased blood potassium. I haven't been eating enough potassium in my diet, and my blood potassium is low. How is that going to affect resting membrane potential? That's the question. What's going to happen to resting membrane potential? Really, our options are, if we try to graph this out, we are down here at minus 70. Do we go up? In other words, do we begin to depolarize? Do we remain constant? Or do we hyperpolarize? Those are our possibilities. We'll label them A, B, or C. And our job is to try and understand what happens. So in the case of hypokalemia, which would you predict? Would we hypopolarize or depolarize, hyperpolarize, or remain constant? Well, let me tell you how I begin to answer these questions. Going back to our picture, we know that the gradient for potassium is high on the inside, low on the outside. If we graph that in a certain way, graphs are helpful visual tools. So let's consider a simple bar graph where this represents the inside, this represents the outside, and this represents my concentration of potassium. And what do we have on the inside? We know we're high. And on the outside, we know we're low. This does a really good job of defining the steepness of the gradient. This shows us the slope. Of course, the steeper the gradient, the more desire there is to move. The more shallow the gradient, the less desire there is to move. So in this case of hypokalemia, we're talking about the outside, and we've actually decreased the amount of potassium on the outside. In other words, instead of a bar that's this high, we've only got a bar that's this high. And we see what that does to the steepness of the gradient. It made it steeper. So what happens in hypokalemia? A steeper gradient simply means more potassium leaves over a given time. And like we said at the beginning, the more potassium that leaves, the more negative the cell gets. So which one is it? For hypokalemia, the answer is C. The more potassium that leaves, the more negative the cell gets. This leads to a hyperpolarized state. Now, if that's the case, then we should be able to make the argument that for hyperkalemia, we should see the opposite. So let's go back and let's graph it out. For hyperkalemia, that means we have more potassium on the outside. Let's go ahead and graph that. Let's say we have that much potassium. We see indeed that the steepness has become less. This represents a more shallow gradient. In other words, the desire for potassium to leave is less because the strength of the gradient is less, and potassium being or wanting to leave less leaves less. And if less potassium leaves, then what happens? The cell becomes less negative. In other words, it depolarizes, or it becomes, I can't say more positive, it's not going to get positive, but it is becoming less negative. So a shallow gradient means less potassium leaves, and this means the cell depolarizes. All right, let's choose another ion and see how this might affect resting membrane potential. Let's now look at sodium. And let's say hypernatremia. This is going to be increased blood sodium levels. Well, if we go back to our picture, in fact, we could make another graph. This graph is going to be just the opposite, right? Where we still have in, we still have out, We still have over here, instead of potassium, we have sodium concentrations. And at rest, we have a little bit on the inside. We have a lot on the outside. But in this, and this defines the steepness of the gradient, right? The steepness of the gradient is high to low. Sodium wants to go in. So we're looking for hypernatremia, high sodium on the outside. Well, look what happens here. If we increase the amount of sodium that's on the outside, what have we done? We increase the steepness of the gradient. In other words, sodium wants to get in more. So how's that going to affect resting membrane potential? What do you think? A, depolarization as sodium goes into the cell. B, nothing. Or C, hyperpolarization. The answer is B. Why, you say? Sodium's a positive ion. As it moves into the cell, it would depolarize the cell. And in that statement, you're absolutely right. But let's go look at our cell. Are there any doors open for sodium? The answer is no. We've got a sodium-potassium pump, but it's not affected by gradients. It's got an ATP-driven mechanism, and it's establishing the gradients. If I were to open a door, sodium would definitely rush inside the cell. But there aren't any doors open for sodium. So it doesn't matter if I change sodium concentrations for resting membrane potential. Now, as a prelude of what we're going to talk about next time, certainly the action potential is dependent on sodium gradients. Certainly changing sodium concentrations would affect the action potential. But for natremia, for hyper or hyponatremia, sodium doesn't affect resting membrane potential. Neither does calcium, neither does magnesium, neither does chloride. There are no other doors open at rest. The only ion that's allowed out of the cell or into the cell is potassium, and that's the magic of resting membrane potential.